Right, here's our video today, calculating star distance and using parallax. And parallax, in simple terms, right, it's just a way of measuring how far stars are to us, or planets. And para, if we break this word down, para means, it's a Greek word, means besides, next to, right? And alaxis, part of the Greek word, is to change or to shift. So in this video, we're going to use our closest star to our sun, which is Proxima Centauri. So let's write that down. We're going to be talking about that. So we're going to use parallax to find the distance to Proxima Centauri. So let's write it here, Proxima Centauri, which is a red dwarf, smaller than our sun. And the thing about Proxima Centauri, it's in a trinary system with three stars, or Proxima Centauri, Alpha Centauri A, and Alpha Centauri B. And so they all, imagine having three stars in the solar system. But nevertheless, how does it work? That's what we're going to talk about in here. Because we have no gigantic tape measure, right? We're not going to take a tape measure and go from Earth to Alpha Centauri or Proxima Centauri, which with our technology that we have today would take us over 70,000 years. So we don't have a tape measure. So we're going to use trigonometry. We're going to use math. And we'll do that in this video. So in simple terms, astronomers, or you, or Aunt Sally, somebody, we're going to measure a star from different points on Earth's orbit, 6 months apart. So basically, right, we'll have that as the Earth. Try to make a circle today. Right? So we'll measure Proxima Centauri. Let's change the color. Let's say use yellow. So from one point here, and then 6 months later from another point on Earth. Right? So let's say, maybe in New York City, somewhere in New York City, maybe Brooklyn, Long Island, somewhere. And then maybe in Spain. Maybe Madrid. So we're going to be measuring Proxima Centauri. So let's get a better page here, clear page. And again, we're going to measure the distances we're going to measure an angle to Proxima Centauri 6 months apart. Well, actually, we're doing it in seconds today. So let's create. Let's say, and we'll use yellow. Right, our sun's a yellow dwarf. So let's just say here's the orbit. Here's the orbit of the Earth. And we'll have our nice star there, our sun. And we'll have the Earth here, and we'll have the Earth here. And over here we'll say, well, let's say that's the Earth in January. And over here we'll say the Earth in June. So at different positions in its orbit around the sun. And then over here, for the red dwarf, we'll have Proxima Centauri. So this is our star, Proxima Centauri. And so when we're looking at Proxima Centauri, let's say here it's New York and here it's Spain, Madrid, or somewhere. And as we look at it, we can see the angle. If we can create, we just missed it. Gotta practice our lines, right? And then in June, the same thing, boom, right? And so what we did was we created an angle, this angle right here, and we're going to call that angle, that's going to be the arcsecond angle. We'll get back to that. And then over here, the distance from Earth to the sun go back to making straight angles today. So the distance to Earth, we'll write this as Earth to the sun, and the distance, it does vary. depending on the season. But on average, the distance is about 93 million miles. And we'll just say 93 million miles as our distance. Remember, in the winter, in the northern hemisphere, the Earth is actually closer to the sun. But we'll say 93 million miles, and 93 million miles is called 1 AU. And AU means astronomical units. So, because we think we're special on Earth, we say 1 AU is the distance Earth is to the sun, 1 AU. And so, to do this, now we have Proxima Centauri, but we also need distant stars past Alpha Centauri or Proxima Centauri. And we'll say these are distant stars. Stars in the background. And usually you want stars that are very far away, much further away than Proxima Centauri. So, I mean, we could use, for example, Sirius or Betelgeuse, or if you want to pronounce it Betelgeuse, or any other star, but you really want stars that are very, very far away. And so for this video, we're going to use a star called HD, high definition, right? No, 111980. It needs a name. And it's very far away. It's 25,000 light years away. Just imagine this. Light can go 6 trillion miles in 1 year about. So you can imagine how far this object is. So in simple terms, what happens is, as the Earth is moving around the sun, and you look at Proxima Centauri from different locations, Proxima Centauri will shift a little bit. It'll move a little bit, but the distant star, HD 11980, it'll seem like it's not moving. And even though everything's moving in space, because it's so far away, it'll seem like it's not moving. But Proxima Centauri will shift a little from January to June. And it's that shift, that angle that we get, and using trigonometry, that we can find how far away it is. Okay, let's look at it from a different point of view here. So let's say, like, this is the sun. It's wearing green today. And we'll say that's Earth. And that could be Earth again in January. And then as it moves around, there it is in, let's say, July, right? 6 months apart. And so then we have our base of our triangle, right? So again, we said it's 1 AU. On both sides, it's 1 AU. So we're getting 2 AU, astronomical units. And that's about, we'll put it over here, 186 million miles. And then we have our star that we're trying to find the distance, Proxima Centauri. So we'll say over here. And see, we can make a line now. See how we're making this triangle. And we're getting, oh right, I got right to it today. Then we have our little triangle. So we made a triangle, that's why we call it trigonometry. And we're trying to find the distance, D. And this right here, this angle, this is angle P, and that is the parallax angle. Of course, we want half of it in trigonometry. And of course, over here is the distant star. Remember, we say HD, put it over here, HD 111980, or whatever you want to call it. Call it Tim. Maybe Tim, why not? So we know that HD 11980 is 25,000 light years away. And as the Earth, remember that's the Earth over here, as it moves in orbit, and you can see the angle to Proxima Centauri will shift. That's the parallax. It'll shift, but HD 11980 will not move, even though it is moving, because it's so far away. So let's say, we'll cut this up over here, do another view. Let's say that we're looking, here's Earth, right? And we see Proxima Centauri, and we'll make it a red dwarf. We'll see it over here. And maybe we're seeing that in January. And we'll make HD 11980. Let's say it's way over here in January. And it doesn't move. So then in July, when we're looking, let's say we're looking over here now. So let's say it shifted a little. It shifted here, let's say. Let's just say it's shifted there. So as you can see, here's the shift. It's shifted. And that shift creates that parallax angle right over here. Now, there is a formula for this. The distance is going to equal 1 AU, which we already know what it is, divided by P. And P is the parallax angle. And thank you for all those astronomers who calculated this. The parallax angle to Alpha Centauri, the Proxima Centauri, is 0.77. So all we have to do is just plug it in. Now, to get the parallax angle, you have to really take careful measurements. Obviously, you need a telescope. And attached to the telescope, you need this thing called a heliometer. And helio means sun. And it's basically like a protractor. But unlike a protractor, which only measures degrees, the heliometer will measure arc seconds. Because you really need very small measurements. So an arc second measured with a heliometer equals 1/3600th of a degree. It's 1/3600th of a degree. All right, so let's look at this. Let's plug in everything over here, and we'll bring it down here. Follow the arrow. So if we do that, what you'll get is it's 1 divided by 0.77. 1 divided by 0.77 will give us 1.3, and it's in parsecs. 1.3 parsecs. Now, what's a parsec? Well, a parsec is equal to 3.26 light years. And again, a light year is how far light will travel in a year. And basically, it's a little more, but it's about 6 trillion miles. About 6 trillion miles. It's less than that, actually. So, if we know now that Proxima Centauri is 1.3 parsecs from us, but since a light year is about 3.26 light years is 1 parsec, well, then we just do the math. That'll mean that keep saying Alpha Centauri, since it's the Alpha Centauri star system, but Proxima Centauri is 4.24 light years away. Now, it takes light a little over 4 years to get to us from Proxima Centauri. But with our technology, it would take over 70,000 years. And if you want to round that up, we're looking at 25 trillion miles away. And there's a heliometer attached to a telescope. So again, as we said, just to review, you're taking 1, because we're using 1 AU, and we're trying to find the parallax degree, which we know is 0.77 thanks to careful measurements, and we got 1.3. So remember, your answer is in parsecs. So if 1 parsec is 3.26 light years, well, then we could just do a proportion and say 1.3 parsecs will equal x, and just do the algebra here, and you know x is going to equal 4.24 light years. So we found the distance to Proxima Centauri. And that's our video today.